Вот теперь правильно. Значит, здравствуйте все. Рад очень видеть всех, кто пришел лично. И рад видеть, точнее, слышать тех, кто... Так, почему? Одну секундочку. Мне нужно мой микрофон отключить. Так, алло? Все еще он не хочет.
Плохо слышно очень.
Одну секундочку, сейчас я это...
Микрофон плохо слышно. Ты там пошевелил.
Да, сейчас я это настрою.
Нет, твой переносной микрофон.
Привет, Вер.
С микрофоном, возможно, так просто...
Так, теперь ничего слышно? Теперь стало лучше слышно?
В общем, микрофон — такая проблема, что он в хорошем качестве пишется, а когда идет зум, он режется. Вот, поэтому, возможно, стоит слушать звук.
Дело в том, что у китайцев YouTube запрещен. Почему мы просили через зум? Потому что в Китае он реально запрещен. Они просто не смогут его смотреть. Там сами жили.
Насколько плохо слышно меня? Я постараюсь говорить как можно медленнее и разборчиво.
Он все время рвется, этот звук.
А
можно ли, например, не транслировать?
Можно транслировать звук.
Это проблема не из трансляции, а из-за того, что звук тут в высоком качестве. А когда звук транслируется, он режется.
Можно тогда скинуть ссылку всем желающим на YouTube, чтобы они задавали вопросы в Zoom, а слушали лекцию непосредственно на YouTube.
Не смогут они слушать.
Да, это верно. Спроси, может быть, у этих граждан есть какой-то VPN, они все-таки...
Ты же помнишь масштаб?
Я помню. Но спроси у присутствующих, может, какой-то VPN у них. Прошу прощения за технические сложности у всех. Это... Наладить трансляцию с первого раза не всегда удается.
Дайте я им напишу просто. Сейчас,
Саша. Что написал? Значит, я правда не знаю, как что делать со звуком, потому что включать второй микрофон я, конечно, могу, но тогда будет ужасное эхо, как я понимаю.
Нет, так сказать, вот этот микрофон, наверное, можно замьютить, наверное.
И говорить через телефон.
Говорить через телефон.
Тогда я подключу.
Да, вы замьютите?
Давайте. Тогда подключу свой телефон. У меня в кармане полежит, ничего с ним не будет. У меня есть гарнитура, да. Рождественская елка. Спасибо. Это я сам уже. Спасибо. Да, там он включен, скажите просто, Миша, или вы выключили? Сейчас я его включу, когда... он включен. Вот написано mute.
Да, все нормально.
Он включен.
Я просто из зума выключу вас.
Так.
Вопрос поставил в тупик, они ничего не отвечают.
Какое?
Что не могут, потому что это там реально очень сложно.
Да, я помню. Я помню, ну, то есть народ, конечно, придумывал способы, но...
Нет, знаешь,
там...
ссылка есть?
Так, Саш, скажи, теперь меня слышно? Я сейчас... я должен свой микрофон отключить. Подожди секунду. Теперь слышно меня?
Да, теперь слышно, да.
Я, наверное, даже буду слышать, если вопросы, если кто-то будет задавать. Скажи просто что-нибудь в микрофон. Ага. Так, тогда мы начнем, в самом деле, наш рассказ. Я только, наверное, включу свой микрофон. Саша, проверь, пожалуйста, как работает твоя, как он называется, твой микрофон, чтобы я слышал, работает у меня. Да, работает. Угу. Хорошо. Так, ну что, давайте опять начнем. Теперь уже, надеюсь, окончательно. Значит, что предпочитаете все? Значит, у нас, на самом деле, тут в аудитории в Москве собрались люди русскоговорящие в основном, а слушают нас люди не русскоговорящие в основном. Поэтому вопрос к присутствующим. На английском можно говорить или это что лучше?
Нет, но если они не русскоговорящие, если ты будешь говорить на русском, это бесполезно. Поэтому придется говорить по-русски.
Хорошо.
Из уважения к этим людям.
По-английски, то есть.
Конечно, там не говорят по-русски
Если
вообще.
может по-китайски.
Окей. Китайский я знаю только одно, только нихао. Больше ничего. Хорошо. Okay, let's speak English then. So the general vote was for speaking English, and I switched to the English. The purpose of this seminar is to give the audience who attended first some introduction to the interesting set of topics centered around non-commutative algebra and non-commutative geometry, roughly speaking. So that's the first purpose. So give introduction to the non-commutative algebra and geometry and their application. And geometry with applications. And the second purpose, the purpose is twofold. The second part of the purpose is to allow the audience, to give the audience some opportunity to investigate some parts of these topics which are interesting to them on their own accord. So to say, if you're interested, if you find that some of these subjects call to you more than the others, you are free to choose them and prepare a short talk of your own, so that if you are, for instance, a PhD student or want to be a PhD student, this talk can be regarded as some introduction to your personal and scientific investigation. So it can be part of your scientific investigation, you can starting point of your scientific investigation. So talks by the students. So that's the purpose of the first. Okay, so that's the purpose of our first meeting then, is to delineate the subjects we are going to discuss and to give some introductory explanations concerning these subjects. So it will not be very deep, it will not be very hard, it will not probably speak about something which you have never heard of, but I just hope that you will have some impression of what they are, of what the subjects are, what that we speak about, and also, and in the end, I probably give a list of topics which we are going to discuss in future. So I begin with something very simple. Sorry?
Техническая проблема, потому что там у них расплывается изображение.
Ah.
Можно чуть-чуть почетче.
I see. Okay, I'll try to write with larger handwriting, in larger script. Definitely, yeah, I see. I see. I try to use larger script, at least when it comes to some formulas. I try to write large. So we begin with something very simple and very elementary, which everybody studies at school. Suppose you have a point P. Sorry, a point with coordinate P. Sorry, with coordinate Q. And it is acted upon by a field, by some force F. So you can imagine that everything, everything goes on a straight line. So as probably everybody knows, the Newton's equation is that the acceleration of the point, that is the second derivative with respect to the time, is equal to f times mass, the mass of the point. But I'll assume that the mass is equal to 1. Right? So this force depends on the point, on the position of the point Q. Let's assume that it only depends on the position of the point. And as such, we can choose a potential function u such that this force is equal to the derivation of u with respect to q. Okay, let me take a look at my notes. Yeah, sure. So this is not a problem. Problem is that I want to make certain transformation, and I want to make it correctly at the very first instance. So what we do now, we consider the impulse of the point, the moment of the point P. It is equal to q dot, and maybe we need to introduce mass, but the mass is equal to 1. So what we have here is P dot is equal to minus u of q. Okay. Now let us multiply both sides of this equation by p. P dot p. Sorry? Yeah, prime. And here we have minus u prime times p, which is just q prime, q dot, right? So that's what we do. Now we can integrate both sides of this equation. And what we have here is p dot square divided by 2, is equal to d over d dot, d over dt is equal to d over dt of the function u of q minus. So that eventually we have the following equation: d over dt of p dot square divided by 2 plus u of q is equal to 0. The function which we have inside our parenthesis is called the Hamiltonian function. It actually appears much more often than just in this silly equation, very simple one. And we regard it as a function of p. No dot here. No dot here either, sorry. It's a function of p and q, right? And of course, the first thing which we see at once it is that this function is preserved in time. So it is some kind of first integral of our process, of our dynamical system. But this is just a very small thing to consider. So what we can do further, it is that actually we can now describe the dynamics of our system in terms of this function h as follows. P dot is equal to minus u prime, right? And it is equal to so if we now differentiate h with respect to q, we obtain precisely this, only with the sign, right? So this is precisely this equation. And also q dot is equal to p, as we know. That is the way we introduce this new variable. So again, it is equal to dh over d p. Now, of course, this can be generalized to the system which lives in the space of arbitrary number of dimensions, of arbitrary dimension. So we can just put I here, and then we have Qi here. The reasoning is done in precisely the same way. Now P and Q are elements in Rn, so the pair P and Q lives in R2n. So actually, it is not necessary to begin with this kind of Newton equation. I don't know it is necessary to make this exercise or not, but actually, observation. Under very mild assumptions, the Euler-Lagrange equation can be rephrased in terms of Hamiltonian equation. Every Euler-Lagrange equation under mild assumptions, well, say it is smooth and so on. And as everybody knows, modern physics is usually phrased in terms of some minimizing principle. We have some Lagrange function, and we need to minimize the action of our process along the path, and that will give us the correct path of our process. So that's what we do here. And it turns out that very similar formula appears. In that case, you can actually write down the Hamiltonian function in terms of Lagrange function, and with the help of is it Legendre transformed? Yeah. So actually, if you have Lagrange function L of q dot that is P and T, then the Hamiltonian function is just P T is just sum over I Pi Q I dot and minus Lagrangian. Sorry. So we go on. The purpose of considering this equation is to rewrite it even further. Actually, what we do, we introduce the following algebraic structure on the space R to N. It is called symplectic structure. And we shall rewrite these equations in terms of this new structure. Namely, let us consider two functions f and g, smooth of two n variables. And we shall denote by the, how do you call this, the figure bracket, the fancy brackets of f and g, which are called the Poisson bracket of f and g. The following sum. The sum is taken over I from 1 to n. We take partial derivations of f with respect to p, I believe, I, and multiply by the partial differentials of derivations of g with respect to qi, and subtract the opposite product. In this case, this equation can be written in a very nice way. Namely, you just observe that P dot I, it is equal to minus dH over dQi, right? And now I'm just confused a little bit about the sign. The sign is a little different from what I have chosen, but let us try to guess it. So we need to put h either here or here. I think it should be put here. No, on the left. H and P, I believe. Yeah, like this. So if you look at this formula now, then this term will be constantly equal to 0, and this term will give you precisely this partial derivation. And similarly, Qi is equal to h with Qi, the Poisson bracket of Qi with the same function h. In fact, for any function f of p and q, we shall have the following equation. If we take p of t and q of t to be the trajectory of our dynamical system, then df dt, where we got df over dt, where we regard p and q as functions of t, will be equal to the the Poisson bracket of h with this function. So this is a way to consider any evolution of any physical value which you can observe at your trajectory. Now, of course, this is very nice and good, and now, well, I'm not going to go deep into the symplectic geometry, which actually studies these kind of things. There is a very nice way to describe the integrability of dynamical systems in terms of functions. We shall speak about this a bit later, maybe, but not today. For me, the principal structure here is the Poisson bracket. So Poisson bracket actually verifies the following set of conditions, which I recommend to check by hand. Almost all of them are evident, except for the last one, which is also very simple, but you need to think a little bit. So the first condition is that it is skew symmetric. The second condition is that it verifies the Leibniz rule with respect to its arguments. Actually, I'm only writing for the second argument, but of course, since it is skew symmetric, it verifies it with respect to both arguments. And finally, the most difficult, the most interesting part of these properties is that it verifies the Jacobi identity. So, namely, if you take double bracket of f, g, and the third function h, and take the cyclic permutations of all these functions, that is to say, g, h, f, and finally h, f, g, and what you get is 0. So in order to prove this, you can either just expand this definition and check that all the terms will cancel out, will kill each other, or you can use this property and reduce the number of things you need to check, reduce it considerably, just reduce it to some very simple functions which can be done by hand. Okay.
Maybe it is worth mentioning that the brackets is
linear, yeah, sure. They are linear. So this Leibniz rule actually amounts to linearity when the function g and a or h is constant, yeah? Because this is a kind of differentiation, and when you have a differentiation, it is always the case that the derivation of a constant function is 0. It is just a property of differentiation. So yeah, it is also worth trying to prove this by hand. Yeah.
No, I mean you have f and g plus h.
Yeah, sure. Yeah, sure. Sorry. That's part number 0. That's 0. Yeah, sure. Yeah. Right. That's 0. F g plus h. It is additivity, right? F g plus f h, and this is so simple that I even forgot to mention this. Okay. So what is the purpose of using this? The purpose is just to mention that all modern physics is usually, well, is very often phrased just in these terms. At least so it was before the creation of quantum physics. In 19th century, people believed that we need just to solve certain usual differential equations or partial differential equations, and then we are done. We know everything which goes on in the world. But then, in beginning of 20th century, I think it was Max Planck who first observed that in order to deal with very small objects of the size of an atom, or the size of atom's kernel, right, core of the atom, you need to introduce different principles. And these principles, there is a way to justify them from some experiments. If you want to look at these experiments, you can open for instance, Feynman's lectures on physics and take a look at the place where he describes a very famous experiment with electrons being dispersed over one or two narrow gaps in a wall, right? So this experiment actually shows that electrons, even though they are thought of as particles, the way they behave is more like the way waves behave. And this brings us to the so-called particle-wave duality, or how do you call this in English? I don't know. How do you call this in English? Is this the way you pronounce it? Never heard this, actually, being a mathematician. And makes the whole business much less dull than before. The principles of quantum mechanics, which were elaborated in the beginning of the 20th century, are as follows. First of all, the behavior of particles, of quantum particles, is described by wave functions So there are different ways to think about wave functions. For me, they are just some functions on the space where these particles live, so to say. That is done because this is so because the most widespread, the most agreed upon explanation of these functions is that so these are complex valued functions. So I write them as C infinity, but actually they should be either rapidly decaying functions or they should be functions with compact support or something like that, so that all our integrals should converge unconditionally. So you have some smooth functions psi on the space where we live, R2n, for instance, right? Sorry, on Rn, yeah, because R2n is I don't want to add momentum at once, so they should live just on this space. And so they are complex valued. And then if we want to know the probability, the integral over the whole space of the module of this function is equal to 1.
Square.
Yeah, square, right. Thank you. You know more than I do. You remember better than I do. And if you want to know the probability that your function lies inside certain neighborhoods and there's a certain domain omega in Rn, then the probability of the function being there is just the integral over omega of the same value. Right? So this is the way you interpret particles and in terms of functions. So we don't work with particles as some points in the space. These particles are distributed all over the space. We just can speak about the probability of finding a particle in a certain part of the space. And that makes many physical and very nice many physicists and very nice physicists quite uneasy. I think it was Einstein who said that nature doesn't play dice with you, right? Doesn't gamble. And this is quite the opposite philosophy. Okay, now this is the way you interpret the particles. They are described in this way, and then you need to describe the processes which flow in the world of particles. So these processes are described in terms of functions when we speak about classical particles, right? So that is actually the purpose of introducing this this algebraic structure. You see? Now there is no difference between the values of certain functions that we see and the process which is induced by this function, right? So we have a function h. We can speak about values of this function, but we can also speak about the process, the dynamics which is induced by this function h with the help of symplectic structure, right? That's what we do. And that helps us very, very much when we speak about quantum particles. Namely, for us now, the processes and the functions, observable functions on the space of particles are just operators. So observables, operators on the space of functions, space of wave functions. If we want to know how the value of this function, then we can do this again by pairing our function with the wave function. So pairing our operator with the wave function, and then taking the integral. Namely, let me again take a look at my notes, lest I make some stupid mistake. So actually what we are interested in is the expectation value of our function, of our operator, of our observable f. So this is observable at the state, at the wave function psi. It is just the integral over omega, so again inside omega, of psi bar f of psi d mu. As you see, once again, we cannot speak about the value of function, the value of observable at certain particle. But we can speak about the mean value of this observable at the part of the particle which falls inside the domain in the space. So it is a little bit tricky somehow, but so it goes. Now the most important part of the whole business is that we now need to introduce the flow. We need to introduce the evolution of our particles and of our observables. Yeah. So actually, once again, there is no difference now between flows and functions. By the way, in particular, we can speak about the observables which correspond to the coordinates of our particle, and to about the observables which correspond to the momenta of our particle, right? And that's also encoded here. Now, in classical case, we had the following formula, which I have erased somehow, but let me restore it. df over dt is equal to the Poisson bracket of h, the Hamiltonian function, with f And this formula actually describes the behavior of our system completely, because if we put, for instance, f to be equal to the coordinate of our function, then we just obtain the usual Hamiltonian equation, right? And this is more general. Now, the analog of this formula in quantum case is taken to be the following. I think it is Heisenberg equation, right? Or Schrodinger. I always forget what is difference. I think it is Heisenberg. And Schrodinger, I am going to write down Schrodinger a little bit later. So Heisenberg equation is, I'm omitting the coefficients which usually appear here, just make them enter the Hamiltonian function h. So what we have on the right is just the commutator of two operators. You have an operator f, which corresponds to some observable function. You have operator h, which corresponds to another observable function, which we call Hamiltonian of our system. And then we have this kind of Heisenberg equation. If we want to speak about the way the wave function behaves, then we can actually think about this as an operator and try to apply this operator to the wave function, right? Now this wave function can depend on time, and after very few transformations, you obtain the Schrodinger equation, again up to the coefficients. It looks like d over dt of psi is equal to minus I divided by h of psi. And this h, I, and they are just very renowned coefficients, so I didn't dare to erase them here. But of course, you can absorb them into the Hamilton function, into the Hamilton operator. There's no need to be so picky. So we have a very nice picture. And there are lots of things you can do with it. You can, for instance, prove uncertainty principle. That is the famous observation made by physicists in the early 20th century, that you cannot actually determine exactly both the momentum and the coordinate of your quantum particle. You can only determine either the one or the other of them. The more accurately you compute the momentum, the less you know about its coordinate, and vice versa. The opposite is also true. You can also prove many other things, but what is really important, it is the way you introduce these operators. So now the main question of the whole business of this sort is, how do you choose your operators? I mean operators which stand instead, which you take instead of your observable functions. And to answer this question, we need to have some principle which will tell us which choice is correct and which is not. And unfortunately, there is no good principle so far. The most usual way to do this is to say, so example which is actually very widespread and most commonly used. We observe that if we have Pi and Qj, and the take their Poisson bracket, then what we obtain is just delta ij, the Kronecker symbol. And that on the other hand, from this very simple relation, one can restore the whole formula for the Poisson bracket using the fact that it is Leibniz rule, so that it verifies Leibniz rules and all the other conditions that we have, right? So the Poisson bracket can be restored from this very simple principle and from the properties of the Poisson bracket. Now, so this is a classical side, classical. On the quantum side, people say that instead of the momentum and coordinate of our particle, we consider their quantum analogues, operators pi and qj, and then we ask this commutation relation to be equal to delta ij again, maybe times certain coefficients, renowned coefficients, which we actually again absorb into one of these operators. Okay? And then the hope is that we can now restore all the other operators very simply, and all the other brackets, all the other commutators very simply from this relation and from any nice choice of momentum and coordinate operators, just using the formulas, right? However simple this principle might seem, it has lots of problems. For instance, I forgot to say that these relations are called canonical commutation relation, yeah? Canonical commutation relations. One of the problems which appear at once as soon as you try to work with this pair of operators is that it is impossible to choose as operators that both of them are bounded in sense of Hilbert space. So all operators usually are thought of as operating on Hilbert space, and actually what we did when we considered the mean value of our psi, we actually considered its Hilbert square, right? It's scalar square inside the Hilbert space. So it is natural to expect that we shall work with bounded operators, but this relation prevents us from taking bounded operators. So the problem number one is that they are not bounded. Not bounded. So, but this problem is of some analytical nature, and if it were only for this problem, it wouldn't be that interesting for me, at least. Now, the main problem is that if we work with functions which only depend on p and q, so that p and q do not appear in the same formula, there is no problem with choosing the operator which correspond to these functions. For instance, the original Hamiltonian functions which we considered looked like p squared divided by 2 plus u of q, right? Now, the quantum analog of this Hamiltonian would look like p capital squared divided by 2 plus u of q capital. Well, whatever you define and understand as the function of certain operator, whatever you think about this. If this u is just a polynomial, then there is no problem. You can just take the same polynomial of the operator, but if it is a little bit more different, then you need some operator, functional calculus of operators, but that's doable. This is an analytical problem. But fortunately, not all functions have this very nice property. For instance, if you take something like p square times q square, then in the classical world, there is no problem to write this formula. But in quantum world, you can write it in, let me see, how many? 1, 2, 3, well, at least, I think it is 8 different ways, right? Let us see. P square, Q square being the simplest. And you can also write it Q square, P square. This is a different, right? Because they do not commute. Now you can also write it as P Q square P, or Q P square Q. And also you can write it as P Q P Q. And also you can write it as Q P Q P. Is this all? Maybe all. Then it is only 6. But 6 already is more than enough. 6 different ways, and these operators are all different. They differ by certain operators, not just by constants. So that makes the choice of operators somewhat delicate task, even algebraically, not just analytically. Fortunately enough, people are able to find several nice ways to introduce these operators. The most classical one is again called canonical quantization. And again, if we omit all analytical problems, it looks as follows. So let me take a look at my notes, lest I would make some mistake in coefficients, like minus, I forget to use square root or something like that. So anyway, yeah, here it is. We can see that the Fourier transform of our wave function, so phi is a wave function. We shall assume that phi is a rapidly decaying function. We can assume that phi is in, say, Schwarz space of rapidly decaying functions on Rn. Then what we have, the Fourier transform of phi is just something like this, a square root of 2 to the power n, pi to the power n, integral over Rn, phi of xi, e to the power minus x xi d xi. This is a function of x. This transform sends Schwarz space to Schwarz space, as one knows, and it has inverse. The inverse can take. Oh yeah, I have it, but it's very. The problem is that the font is too small; you just couldn't see it. Sure. Yeah, the inverse is given by the same formula, almost the same formula, only this minus sign in the exponent is changed for the plus sign. As you probably know, one of the wonderful properties of Fourier transform is that it intertwines multiplication with differentiation. And that gives us the following idea. You want to differentiate your function over, say d over dx, right? And then you replace it by f minus first, I think. Then you take x times your function, but not function, but f of function. And what you have is just up to some constants, up to some multiples, the partial derivation of your phi in respect to this coordinate x, right? On the other hand, you have a very nice commutation relation of the operator d over dx and the operator x, which consists of multiplication of your function by the coordinate x. And this is precisely what we need. It is 1. If you have I and j here, then you have delta ij, precisely. Just what you need, right? So this makes us, this gives the following formula. Sorry, this justifies the following formula, which is called actually the canonical quantization formula. Suppose I have an element A in space of smooth functions of R to n, precisely the space of observables, right? So we have observable function in this usual sense. Then you take the following composition, f minus, so you want to define the operator dependent on A on the space of all smooth functions, or say better, Schwarz functions of Rn. Yeah.
I think d over d, not d over dx, but d over dxi.
The problem is that f phi depends of x. And sorry, yeah. The problem is that yeah, phi depends on x, so I cannot just apply d over dxi here, right? I just cannot apply it here. It is right that if I want to multiply, you're right that if I want to restore the original coordinate x here, so suppose you have x here, phi of x, then when we apply f, we shall obtain function of psi. So then you are right, we need to put psi here, right? If we begin with x and end with x, then we have to put psi here, right? In this sense, you're right. Sorry for being a little bit. What else? Oh, yeah, it's over dxi. Yeah, it's just misprint. Yeah, difficult to take care of all this function.
It's a bit inconsistent because the left side phi depends on psi. So
Yeah, right. On the left we need, yeah, sure. Now we have everything in control, yeah, under control. So what we do now, we have this operator, and this operator is actually very easily written. We just take operator of A and apply it to phi, and you want to compute it at point x, and what you get is just f minus first of A of x psi times f of phi. I think it is this, right? The only difference is that x plays the role of the coordinate here, and psi now plays the role of the momentum. Okay? There is a very explicit formula in terms of the integral for this operator. For instance, it is like this. Okay, of phi at point x is equal to 1 over 2 square root of 2 and pi n. Oh, again, I am not sure. I think there is no square root, just this. I'm not sure about this. So it is now integral over R2n, right, of e to the power 2 pi I x minus y psi a of x psi phi of y dy dxi. Okay? A very explicit formula. Now it seems that we are done, and the only problem we have is analytical. The problem, well, it's almost so. The only problem is that these analytical problems are so huge that it is, in many cases, it is much more convenient to consider more algebraic constructions. And even if you forget about these analytical problems, there is another algebraic problem still with this formula. And this algebraic problem is not so evident as it may seem, but let me just mention this problem and then write down the formula which rules this problem out. The problem is that if you take a function a which has real values, so let a be a real valued function, then it is natural from physical point of view to expect that the corresponding operator will also be in some sense real valued. And real valued operator, from the point of view of those expectation values and so on, is the operator which is self-adjoint. So we expect that the operator of A is self-adjoint. And this is not the case here. If you take a look at this operator, then you shall see that, for instance, if we take the function a of pq equal to, say, p times q, then what you obtain will not be self-adjoint. It will be something which adjoins to something different. And it was Hermann Weyl who first observed this problem, and he also gave the solution of this problem. Actually, he wrote down a very explicit formula for the operator which gives self-adjoint operators for real valued functions, and this is the following. So W stands for Weyl, and this is Hermann Weyl, not André. Phi at point x again. Now the formula is a little bit more tricky and not evident to find, but still they say, the legends have it, that some analysts who are very well versed in dealing with this sort of integrals can prove this formula by direct computation, that it gives self-adjoint operators for real valued functions. I can only give this with some help of some trick, prove this with help of some trick. So like this, x minus y times xi, so far so good, but then comes the following trick, which is really unexpected. Instead of integrating over x and xi, we integrate over x plus y divided by 2 and xi. And then we have phi of y dy dxi. So this is the Weyl formula, Weyl integration formula. Again, this formula is even more complicated than the original one. I didn't even write down the coefficients which there should be. I just omit them. So working with this formula directly involves both analytical problems with convergence and so on, but lots of algebraic problems with transformations of this very long integral. So, and now the story becomes much more algebraic, because I really want to get rid of all analytical problems and only speak about algebraic problems, which are already plenty there. And to pass from this analytical formula to some pure algebra, we need to invoke the works of I think it is Enrique Moyle. And also, what was the other guy? So it was, let me see his name. It was Moyle and I don't see this. Oh no, I don't see it. It's probably Grunewald. Grunewald, don't remember this. Who? Yeah, anyway, there were two authors, two guys who observed this formula. The most famous one is Moyle from Argentina, and the other guy was some German guy. I believe the problem why he is not so well known is that he was from Germany, and it was shortly after World War II, so Germany was extremely unpopular at that time. Yeah, I think it was, Grunewald, something like that. Grunewald. I'm not sure. I need to take a look. I have it somewhere, but cannot find it in my. Grunewald. Yeah, sorry, Grunewald. I found it. Grunewald. Hilbrand Grunewald. Jose, not Enrique, but Jose Moyle and Hilbrand Grunewald. Now it's nice. Okay, at least everybody is mentioned, deserves to be mentioned. So what did those guys do? They actually transferred the problem from analysis to pure algebra with the help of some, let me see, say some trick, some mysterious computations. Namely, what they just did, they took this Weil quantization formula and they said, suppose we have two operators. One of them comes from the function A as before, and the other one comes from the function B as before, but the same formula. When we have two operators, we always can take their composition. And let us check if this composition is again an operator of the same sort. Well, of course, in general case it's not so. In general case, you only obtain a asymptotical formula for this operator. This operator is kind of sum of operators of higher and higher degree, of higher and higher rank. But this explicit formula for this asymptotic expansion can be written in a very nice analytical algebraic way. So I denote this expansion with the help of star. And then this star can be written very explicitly. Let me, yeah. Here it is. So this expansion is very explicit. A star B is equal to the sum over k from 0 to n. So we begin with some finite sum, because I mentioned that it's only asymptotic expansion. So I take the asymptotic up to degree n. 1 over 2 to the power k. Then we have the sum over all multi-indices I and j, such that their total value, total model is equal to k. So multi-index I is just a set of indices I1, In, which are non-negative integers. And same for j. Now the only difference is that now you write j here instead of I. Right? Now you have, yeah, module I is just the sum of all ik's. Now we have the following. Minus 1 to the power module j divided by I factorial and j factorial. Now I factorial is just the product of factorials. I1 factorial, In factorial. But that's not all. In the end, you have very nice operator. So first you take the operator. I'm skipping very many coefficients, so just write it as d over d psi. So d psi is operator d over d psi 1, d over d psi k, so one of these operators. And when I say d psi to the power I, it is just the product of d psi 1 to the power I1 and so on, d psi k to the power ik. Okay? And same for dx. So now the formula looks like this. d psi I d psi dxj of A times d psi j d psi dxi of B. And now there's also some residue of higher degree, which I don't want to mention, so something very small. This is a asymptotical expansion. Okay, very nice. Yeah, we're almost there, because now we can forget about all the analytical difficulties. Forget about the question whether this function converges to something or not. And just look at this formula as a sum of formal elements. As a formal sum of elements, the only thing we need some formal variable to count these elements, to distinguish between the degree of their smallness, of their infinitesimality. We introduced this formal variable here. It's actually this formal variable, so it's h to the power k, of course. Actually, it should have been in our formulas if I actually kept trace of all those square root of minus 1 divided by h in all the formulas which I wrote before that. Actually, you remember that I said that the commutator of p and q should be not just delta ij, but delta ij times square root of minus 1 divided by h. So if I kept trace of this h everywhere, then this h should have appeared. But now, this h here in the original problem had the sense, was just this very small real number, the Planck constant. And here, in this formula, just a formal variable. And what we obtain in the end is just the formula which is called the Moyle quantization formula. So, Moyle product formula. So I just write down this formula and explain how this formula is actually just what we have here. So this formula is written in the following nice way. So we have f and g functions, smooth functions on R to n. And their formal product, Moyle product, is just m. So I'll explain all the ingredients here. Times well, let me write it down in two forms. So first I write explicitly. So I have this what is here? Yeah, sum over k from 0 to infinity h to the power k, k factorial 2 to the power k, and sum over all sets of indices I1, I2, IK, and similarly J1, JK, right? They both derive from 1 to n, and there is no actually there's no ordering. They can take any values, and then we take the following. Let pi ij be the matrix 0, 1, minus 1, 0. So the first coordinates I'll denote, so ij, okay? Like this. Now we have the following. Pi I1 J1, pi ik jk, d I1 dik of A times dj1 djk of B. In this formula, I actually reconciled the coordinates x and xi. Here, xi play the role of the first n coordinates, and j and x play the role of the last n coordinates. So I make no distinction between them. They all are called x1, xn, x to n for me. And so I have this formula. So this is precisely this formula, and a more compact way to write down the same formula is to use the following notation. M exponent of pi over 2 times h bar ij di times dj and now we apply this operator to f tensor g. Yeah. Here they k, I1, ik through I1, I2 through ik, and here I have j1, j2 through jk. Yeah, the same here. You see, they appear in pairs. I1, j1, I2, j2, ik, jk. So there is an equal number of i's and j's. Right?
But this key is related to those key in the cell.
Yeah, precisely. Yeah, sure. So this formula is just a formal analog of that asymptotic expansion which we began with. And as such, as formal analog of this asymptotic expansion has lots of nice properties. So first of all, it is associative. F star g star h is equal to f star g star h. Second, f star 1 is equal to f, of course, and equal to 1 star f. However, this product is not commutative.
One more question. What is M?
Oh, sorry, I forgot to say. M is just a product. So I need to explain the notation here, yeah? I'm sorry for this. So notation is very intuitively clear. So first of all, you have a tensor product of two functions, and now you have a tensor product of partial derivatives. When you have two such tensor product of partial derivatives, you can take their tensor-wise, well, leg-wise product and obtain tensor product of partial derivations of second order, and so on. So eventually, when you take this formal exponent, you obtain a formal power series of differential of tensor products of differential operators, right? You obtain a formal power series of tensor products. So it belong to differential operators, tensor differential operators, right? So now when you have this tensor product, you can apply it to a tensor product of functions. The first leg is applied to the first function, and the second leg is applied to the second function. What you obtain is again a pair of functions, is a tensor product of two functions. And then you just take the product of these two functions in the usual sense. So M is just the product in the usual sense of these functions. Okay? So this product has very nice properties. So first of all, it is associative, it has unit, but it is not commutative. In fact, if you take F star G and subtract G star F, then it is easy to see that the first term here is always equal to F times G in the usual sense, and then there comes something multiplied by H, right? So if you expand everything and take the first term in parameter h, we take the terms with h in degree 1, what you obtain is h times the Poisson bracket of f and g. And then there will be some terms of degree 2 and higher of h bar. Right? So these two properties are very nice, and I also observe, before I proceed just a little bit, I'm almost there, I'm almost done with this talk. But before I proceed, I just want to observe that these formulas actually does not depend on the choice of this matrix. I could have taken any matrix, totally any, absolutely any matrix. The only condition is that it should be, well, constant. It shouldn't depend on the points in our space. So if you take any constant matrix and you write down this sort of formula, and what you obtain will again be an associative product with this unit. The only difference will be that here what we obtain will not be the standard Poisson bracket, but it will, some bracket which will depend on the choice of matrix. Namely, if you take, so suppose the matrix Ij is skew-symmetric. Pij is equal to minus Pji. And you can define a generalized Poisson, well, almost not generalized, but let us call it generalized, because today we only have learned about the very simple Poisson bracket. But the generalized Poisson bracket will be just something like f g, bracket of fg should look like sum over I and j, pi j, di f times dg g, dj g, right? Then I think it is a good exercise for you to check that this Poisson bracket will also verify all the conditions, including the condition of Jacobi identity. Now, if the function, so if the matrix Pij is not, now if the matrix Fij is not skew-symmetric, then what you obtain here will be the Poisson bracket induced by the skew symmetrization of your matrix Pij, right? All the products of this sort induced by arbitrary constant matrix Pij are called Moyle products, all these formulas. And these products are algebraic analogs of... Oh, sorry. Okay. Because I'm a little bit tired by this time. Okay. All products induced by various matrices P are called Moyle products. And this gives us some kind of algebra which emerges from analysis. We can now go in the opposite direction and use some analysis from algebra. Namely, we consider a Weyl algebra.
But the result we get the functions in a certain algebra, namely the algebra of formal
Sorry?
power series.
Yeah. So we obtain. Yeah, sure. I just didn't want to make it too much. To give, yeah, to just didn't want to go in through all the details. Yeah, of course, this product is now well defined as an operation on the space of formal power series of variable h bar with coefficients in functions, right?
Write this small piece of blackboard, but
Yeah, I'm sorry, but yeah, sure. The problem is that my handwriting becomes larger and larger with time, and I'm afraid in 15 minutes I'll be barely fitting just one sentence at this blackboard. Okay. Yeah, let's fix this. Yeah. So Moyle products. are operations, associative products on the space C infinity of R to N. Actually, we don't even need to stick to R to N here, because I have ability, I can consider matrices on arbitrary vector spaces, not even dimensional, right? But let's put it V here, right? With coefficients, sorry, formal power series over the variable h bar. I don't want to explain what are formal power series here. It can take us a little bit of time, not too much, but just don't want to. I just want to mention that not all these products are different. Actually, one can show that any two products are isomorphic if and only if the corresponding matrices can be brought into each other by conjugation. Yeah. I think it is still, yeah, I'm just want to make sure I'm not making some stupid mistake here. Yeah. No, even that, worse than that. Not all these products are different. I think it's worse than that. Are different. Well, in particular, you can always assume that the matrix is skew-symmetric. Actually, yeah, just don't want to go into these details. I'm sure that you can conjugate every matrix by something and obtain the same product, but I actually don't want to go into details. I don't have this in my notes. But anyway, I just want to make before we conclude. I just want to make a kind of opposite, a move in kind of opposite direction. So we consider Weyl algebra. Weyl algebra, as you remember probably, is the algebra of polynomials, of non-commutative polynomials over R with two sets of variables, the x1, xn, d1, dn, with only one relation that, well, of course, x1, yeah, with only one set of relations. I mean, of course, xi commute with xj, and di commute with dj for all I and j. But when you take xi and commute with this dj, then you obtain up to the sign probably minus d delta ij. That's what we call the Weyl algebra. Now, Weyl algebra, you can regard it as algebra of of differential operators with polynomial coefficients on Rn, right? Now, of course, it is easy to see that as linear space, this Weyl algebra is isomorphic to linearly, is isomorphic to the space of polynomials of x1, xn, xi1, xin, right? It's just vector space. It's just vector space. Moreover, symmetrization. So you have a polynomial you can write this polynomial as certain product u1 u to the power p1 u k to the power pk, or 2k, sorry, 2n, p2n, right? Where each ui is either xi or xi, right? Yeah, you have every element here can be written in this form. So you can actually forget about, if you allow repeating variables, you can actually forget about these powers and just put it like this: I1, I, G, for some G. So every element here, every monomial in polynomial algebra has this form. And now you can symmetrize it and send every ui to corresponding element in Weyl algebra. You can just very simple-mindedly identify xi's and dj's with these variables, right? Then you can send every monomial here to the sum of all permutations sigma of S G of permutations of G elements like this. That is U I sigma 1 hat u I sigma g hat, where hat denotes the element here. So this gives you a linear isomorphism of this space and this space. Now you can do the following trick. Let's denote this linear isomorphism by S. And you can do the following trick. Take S applied to an element F here. Take S applied to the element G here again. Take their product inside Weil algebra and take S inverse. And you obtain an associative product in this space. And I leave it as an exercise to the audience to prove that this product, well, I forgot to mention to introduce the formal variable h here, but this h actually appears from this relation. Yeah? So that this product is actually isomorphic to the restriction of Moyle product to the space of polynomial functions. So as you see, Moyle algebra encodes both some analytical questions, both them.
One question. The Moyle product depends on pi.
Yeah, sure. And I said the original Moyle product, where the pi is just the standard symplectic structure.
Okay.
Yeah. Yeah, but
It's
here.
isomorphic to the Moyle
Yeah,
product
sure.
on polynomials with standard pi.
Whereas, yeah, sure. So as you see, Moyle product actually brings together an analysis with very subtle analytical properties. And as such, it also involves geometry, because you can actually consider this analysis on curved spaces. In that case, you have to deal with symplectic structures on manifolds and their generalizations, Poisson structures on manifolds. And you can also try to consider similar products for manifolds, right? So on one hand, you will have this analysis on manifolds, which, moreover, analysis of differential operators on manifolds, which involves, in particular, very nice and very subtle mathematical theorems like index theory is some geometric property of differential operators on manifold, right? So Moyle product gives us a bridge between this analysis on manifolds and geometry on manifolds. It gives us a bridge from that very renowned subject to algebra. And vice versa. You can take some algebraic properties, use Moyle product as a bridge, and use these algebraic properties to prove something about analytical properties and the geometrical properties of manifolds, of functions on manifolds, of differential operators on manifolds. Weil algebra is a subject studied very intensively in modern algebra, in pure algebra. Commutative families of elements in Weil algebra is closely related with such, well, hard and long-standing problems in algebra as, for instance, the Jacobian conjecture. And many other conjectures, in fact, are related with the properties of elements, of commuting elements in Weil algebra. Commutative differential operators, elements of Weil algebra which commute, are related with integrable systems. Integrable systems are nowadays classified in terms of commutative pairs or commutative families of differential operators of one or several variables. So our purpose now is to investigate, is to study these these properties from, well, no, I'd say not the purpose. Our dream is to study these properties from all possible points of view. This is, of course, impossible. But we'll try to do our best to speak about this. As far as I'm concerned, I'll try to give some introduction to the geometrical and a little bit analytical part of the story, in the sense that I'll describe the way analogs of Moyle algebras are constructed for curved manifolds and more general structures on them. A very brief introduction, actually, because this subject is also very large. Alexander Borisovich will probably speak about the way commutative differential operators make their way into integrable systems. And now, using this bridge, we can try to use differential operators on manifolds to describe something in integrable systems. That's an interesting question. Also, there is another large subject which I totally missed today. I didn't have time, and I'm sorry, it's too huge to speak about it. I meant the quantum group theory, because quantum group theory is another way which is not alternative. It is analogous, and in some sense it is parallel to this deformation quantization business. Another way of constructing non-commutative algebras from some algebraic and geometric data, right? And one has related to both deformation quantization and also to quantum integrable systems, to non-commutative elements, the commutative elements in differential operators. And I hope Pavel, I'm sorry, forgot your...
It's enough.
Pavel Alexeyevich will speak about, will give some, well, introduction to this subject as well. And either of the audience, anybody in the audience, can make a talk about any subject he or she finds interesting. Yeah, okay, that's all I wanted to tell today. I think it's already more than enough, more than a bit too late to continue.
Thank you very much. Do you have any questions?
Yeah.
Let me precise one technical point. When you were speaking about the connection between Moyle product and Weil algebra, I mean the formula with isomorphisms. You said that you should send some element to algebra, then take the product, and what is a product?
Well, in the middle I have the product in Weil algebra.
You should totally symmetrize
No, it's,
the elements.
no, you're symmetrical.
What is the point?
It's the usual product, the Weil algebra product. You symmetrize elements of F, you symmetrize elements of G.
Yes.
You take their product in Weil algebra.
But
And
Weil algebra is described as an algebra of some generators and some relations on them.
yeah,
So if I take two nodes constructed from these generators, then I should do what?
no, I'm not going to introduce new product on Weil algebra. I'm introducing new product on the algebra of polynomials with the help of Weil algebra. I symmetrize, I take the elements in polynomial
You
algebra.
symmetrize, then put the hats
Yes.
over the elements, and you get some elements from Weil algebra.
Yeah.
Okay.
So you take polynomial, take element from Weil algebra, take another polynomial, get element in Weil algebra, take the product in Weil algebra, and now the miracle happens. Weil algebra is linearly isomorphic to the polynomial algebra. This inverse map is where it's almost impossible to write it down. It just exists, and that's all. It just exists. It's just like Poincare-Berouhov-Bith theorem. The map exists, the isomorphism exists, but write it down explicitly is quite a tricky thing.
There is an algorithm
Yeah, algorithm. You can actually you can find an algorithm, but you cannot find. But it hardly will be a formula. So the claim is that the product you get is isomorphic to the Moyle product. Yeah. Actually, it's something really I know, but I have never been able to prove very accurately. Well, in some sense, there is nothing you can write down except for the Moyle product in that case. So that's it. But the explicit proof needs some work. Okay.
So the answer to the question, so there are several choices. If we consider p square, q square, then there are 6 variants.
Yeah, 6 different ways.
But the answer to this question is just symmetrized.
Well, it is one of the possible answers. There are other possible answers. For instance, there is something they call normal ordering. In physics, it's quite a popular thing. For instance, you choose the formula where all p's stand in front of all q's. That's another way you can do this. But I think if you look at this Moyle product, then yeah, you're right. It's more or less symmetrization. That's a problem. There is no, if you just look at the analytical side of the story, there is no canonical way to choose this product, this formula. Yeah, Weil formula gives you some choice, but it is totally, I say, obscure what it gives in any given explicit case. Probably in case of polynomials, you can elaborate it to something more or less understandable, but it is not easy. Okay. Is this any other question? Is there any? Okay, then.
The only question is, what is the plan for the next time?
Sorry?
What is the plan for the next time?
We shall speak about this separately.
Okay.
I think.
I mean, one of goals.
Yeah, if some.
To invite PhD students.
Yeah, sure.
To make their own.
Sure, but they will need time to prepare a talk.
Yeah, of course.
Definitely. So before that, we shall talk ourselves. We shall make talks ourselves. I think that the earliest date when we can invite students to make a talk would be somewhere in October.
Yeah. Okay.
Before that, we shall make talks ourselves.
Yeah.
Okay.
Could explain us something.
Sorry?
Could explain.
Yeah, you can. Sushi wanted to talk about the Tamita-Takesaka theory, right? Yeah, that's you want. As far as I can understand, this closely related to the non-commutative geometry in the sense of Alain and operator algebra approach to non-commutative geometry. It's a very, very large subject with lots of people working there. Yeah, but so I forgot to mention it as well. Yeah, but next, definitely we shall. If we have time, I'll definitely be glad to have a primer in this direction as well. Okay. If there are no other questions, then I'll probably stop stop this meeting. Okay. Okay. Goodbye then.
Bye.
Oh.
Все-таки накладка произошла. Этот вот магистрант приехал сюда в комнату 310.
Кто?
Ну вот этот магистрант. Ну, не
твой.
нашел там ссылки, там никого не нашел. А я слишком поздно письмо прочитал. Хотя Миша говорил, что он там писал, что все пропало.